12, 11, 10, 9. Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Tower cleared.
We got a roll program.
Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
I hope you got a sense of the enormous amount of energy it requires to launch a spaceship from Earth. The Apollo mission that went to the moon, each of the Saturn V rocket engines were consuming something like a swimming pool full of fuel every minute at the initial part of the launch. It costs a lot of money. It takes a lot of energy to launch a spacecraft. And of course, what we want to do is we want to get it at least into an orbit around the Earth to start with. We need the right orbital velocity. And so we might as well make use of any freebies that we can get along the way, given it's very expensive. Well, if we think about the Earth rotates around in that direction. That's its daily rotation. So 2.1.6, there's really two aspects of the Earth's motion. The first one is the Earth's daily rotation. So we want to make use of that rotation. We want to build our space stations and launch our rockets here as close to the equator as we can to get the maximum boost from that energy. Of course, if we stand on the pole there, all we're doing is rotating around. We don't get any velocity out of that. But if we launch it from the equator, or as close as we politically can get to the equator, and build a safe space station, the more energy we can get from the Earth's rotation. So that's the first aspect of the Earth's motion on a launch, is the Earth's rotation. The second is the Earth's orbit around the Sun. So I'm just going to switch my Earths over and have a look at the Earth here. I'm looking down from the North Pole. So I'm above the North Pole. I'm looking down on the Earth. So if I'm looking above the North Pole, the daily rotation of the Earth is in that direction. And that's why anywhere around here on the equator, we want to build a rocket station there, because we want to blast off and we want to use the velocity that the Earth already gives us, that kind of boost the Earth gives us. And it's quite significant. We want to use that to get ourselves into orbit. But what if we want to go more than just Earth orbit? What if we actually want to go somewhere else in the solar system? Well, that's where we're going to make use of the fact that, this is not to scale of course, that the Earth orbits around the Sun. So again, I'm looking at it as though I'm looking down from the North Pole. And of course, it's anti-clockwise is the daily rotation of the planet on its axis, but its orbit around the Sun is also in an anti-clockwise direction. So if I wanted to launch a rocket into outer space somewhere in our solar system to go and visit another planet, or perhaps to get an orbit around the Sun, which is often the first step, I would want to launch it in this direction here to make use of both the Earth's daily rotation and the velocity of us orbiting the Sun.